Okay, for this section you're going to need your Electricity 2 booklet. If you do not have your Electricity 2 booklet, you'll be able to find it in your Files section in Teams, or I will have also put the link in your chat and you can see it in your chat, and also you can see that it's here, https://drive.google.com, with all this extra work here on the bottom, and that's exactly where your Electricity 2 booklet is. So I want you to have a read of page 11 and 12 now. I will give you 5 minutes. So pause the video and read that, and then come back to the video after reading. Right, now you've read those 2 pages, the next thing you need to do is we're going to have a little look at some of the questions. So the first question here on the next part, it says mains electricity, type of current, what happens to the charge, what happens to potential difference, a diagram, and the type of current. Okay, well that's quite simple, so that last section we don't really need. So let's have a little look at this. Let's use my red pen and away we go. So direct current. What happens to the charge in direct current? So what happens to the charge? It only goes in one direction. Okay, so it's only in one direction. Alternating current changes direction. What happens to potential difference? Okay, this stays constant. In an alternating current, the potential difference changes direction and amount. Remembering it peaks up and down, up and down, up and down. Okay, if we were to draw an axis showing like this, our peak, if it's 230, is up here, but it goes up, changes, it's still going in that direction, but it's less, and then change direction, and then change direction. So that's our alternating current. Okay, so our diagram would be exactly that. Okay, where here is my axis for both of them, and if we put a different colour on there, so let's have a green colour to show direct current. It would be here. Let's say this is 120 volts, whereas this one, our alternating current, goes up and down and up. Oh, didn't go very well, and down. Okay, it should be equal on either side. That just didn't do very clear. And the type of current, obviously, we said here is direct, and here is alternating. Right, let's take it further then. So the next question, what happens to mains electricity? Okay, what is mains electricity? Well, it's 230 volts, it's at 50 hertz, okay, and that's electricity supplied to our homes from the national grid. Okay, Is mains electricity DC or AC? Well, we said it's 50 hertz. That's the frequency of it. Is actually, okay, AC, alternating current, and that is alternates at 50 times a second. Change direction 50 times a second. What potential difference is mains electricity? Well, that one we've already said as well, is 230 volts. And what frequency? Okay, 50 hertz frequency. So that there are questions 1, 2, 3, 4 and 5. Now, the next question, I want to have a go at this question. Let's just move the calculator out of the way so we're able to see what we're doing. Okay, so I'll give you 2 minutes to have a go at filling this in, and then I'll show you the answers. Right, so I want to remind us of our live wire. Our live wire, okay, is this wire here. Our live wire is the brown wire. Our live wire is the brown one. Okay, the brown one goes right. The brown wire is the live wire. So we've got brown. Okay, you know what I'm going to do is I'm going to change that to be brown when we say it. So our brown, we've written in brown. Okay, our brown wire. Our neutral is left and it is blue. And our earth is yellow and green. Our earth is yellow and green. Okay? It's a stripy yellow and green stripes. Yellow and green stripes. Okay, what it does, this one brings the electricity from the power supply. So this one brings 230 volts alternating potential difference to the house. This one takes it away. The earth wire is a safety feature. The potential difference on this is 230 volts. Okay, this is also 230 volts, and this is 0 volts. Okay, so that's our mains electricity. Looking at that, filling in that grid on there. Okay, next, what we need to do is fill in the next section. Oh, we're just double checking. Right, I've actually made a mistake here. Let's go and change that and say that actually that was 230 volts. This one is 0 volts. Okay, potential difference. This is why this one's live and it's dangerous. Okay, the 230 volts is the dangerous one. Okay, that one there, 230 volts. Right, sorry about that, made a little mistake. Next, let's have a little peek over here and see what we've got to be able to do. So what would happen if you touched a live wire? Okay, you would have, because it's got 230 volts, you get an electric shock. Why? It has a 230 volts. Why is live wire dangerous? Even when it's turned off, it's always connected to the grid, to the national grid. Okay? Explain how an earth works to keep us safe. Okay? It touches metal of an appliance. And then what happens next is if the live wire touches the casing, the earth wire shorts the circuit. And what, if you're not sure what that means it stops the electricity from flowing. Explain 2 safety precautions we must take with the live wire. Okay, is never touch it. When the circuit breaker is on. And sometimes we want 2 safety precautions. We might wear gloves, protective gloves. Okay, there's our 2 idea. Now this is looking at the national grid. I want to remind us about the national grid really quickly. That we've got a power station generating potential difference at 25,000 volts. Okay, at 25,000 volts. That then goes up to a step-up transformer. The step-up transformer changes the alternating potential difference from 25,000 volts up to 400,000 volts. And at the same time, the current also decreases, and that's really important. Okay, the current at 400,000 volts, the 400,000 potential difference, and a low current can go across here. Any heat that is created is lost and dissipated into the environment here, and that's where our wasted power, okay, electrical power, our wasted energy, electrical power or electrical energy is being wasted there in the form of thermal energy. It's been dissipated into the atmosphere. What we do to prevent that is we have a higher potential difference, so we can have a lower current. Lower current means that there's less friction in the wire. Less friction means less heating. Less heating means less loss of heat. Okay, the air helps to keep it cool, which is why we have them in overhead pylons. Now also, when we come to our houses, 400,000 volts is way too dangerous, so we drop down using a step down transformer to drop down 400,000 volts to 230 volts, so we can go into our homes. Our factories, however, might only drop to 33,000, okay, or 110,000, okay, volts, something like that. There's a couple of different voltages or alternating potential difference that our factories can have, but our homes it's 230 volts. So what we need to do now is turn to page 14 and 15, and if I give you 5 more minutes in your books to read that page before you do the questions. Okay, so you've paused your video there, and now we're going to carry on and do our question. So if we look over, if you've done the questions, which you should have done, we're going to now go over the answers. So to define the national grid, okay, this is the cables and transformers that take electricity to the homes and factories. Okay, copy the diagram of the national grid and describe the electrical power of the power station and consumer. Okay, I'll allow you to do that, so hopefully you've done that from looking over the previous page. What is the role of the step-up transformer? Okay, take 25,000 alternating potential difference, okay, and step it up to 400,000 volts to make it more efficient. Why is the role of step down transform important? Well, it goes from 400,000 volts to 230 volts. Make it safer. Okay. The next thing, a cable has a resistance of 250 ohms. It carries a current of 40 amps. What power is the cable? Now, remember, P equals I times by V, or P equals I squared R. There are power equations looking at electricity. And we've got an R. Okay. There's our R. And we've also got I in 40. So what we're going to do is use this equation here. That's the one we're going to use. And we're going to get back to having a look at this. So P equals I squared R. We're going to do 250 times by 40 squared. So let's use that. 40 times by 40 equals 1,600. Times that by 250 equals 400,000 volts. Sorry, not volts. We want power, 400,000 watts. So 250 ohms times by 40 squared. That is 400,000 watts. Okay, or 400 kilowatts of power. Okay, what does the power loss take? Okay, what form does the power loss take? Okay, that is thermal energy. That's the heat loss. Okay, dissipated into the environment, so that goes into the environment. What will the power loss be if the current is halved? Okay, so the cable resistance is this, so that's a 400,000 kilowatts of thermal energy lost. Well, if we half the current, okay, so if we've got same resistance, okay, 250, same resistance, but we half the current of 40, so it's 20 squared. We can do that equation here, so 20 times 20, 400, times by 250, okay, equals 100,000 watts, or 100 kilowatts. So if we halved it, we quartered the power loss. So every time we half one, and we call that an inverse square law. Okay, how would I achieve a lower current? By increasing potential difference. Remembering that if we've got P equals I times by V, and if the power that we're trying to supply is the same, a constant, if we want to make that lower, we have to make that higher. Okay, so increasing the potential difference. Okay, 9. If the power of the cables between the two transformers is 14 megawatts, what is the current? Okay. So power is 14. So mega. So we got kilo mega. So our 14,000 thousands. So that's 14,000 watts. Okay. We got I and V. P equals I times by V. We're saying or I squared R. And what do we want to know? What the current? Now we got R equals 250 ohms. Okay, so if we use the equation, P equals I squared times by R. P equals 14 million. R equals 250. So P is 14 million divided by R, 250, equals I squared. Well, let's do that in the calculator to start with. So 14 divided by 250 is 56,000. Okay, and then we square root that. Right, let's have a square root. Square root of 56,236 amps. Okay. Why is it being linked to the UK power station an advantage for customers? Okay. Get direct, instant, cheap, reliable electricity. Okay, and that's it. That is the ad.